Hey everyone, we're going to start chapter 6 with section 6.2. So the first thing I'd like you to do before you watch any more of this video is pause this video, go to chapter 6 tab of OneNote and find this tab that says Derivative Rules Practice. Write down as many of these derivatives as you can, and then when you're finished, scroll down to the second page to check your answers. When you're done with that, unpause the video and watch the rest of it. In this section, we're going to talk about anti-differentiation using a technique called substitution. But before we do that, we're going to talk about something called indefinite integrals. So indefinite integrals are integrals that do not have limits of integration. So as an example, let's say we want to take the integral of f of x dx. Well, we know that we would find its antiderivative evaluated at the upper limit minus evaluated at the lower limit if we had limits of integration, but we don't. So we have the antiderivative capital F of x plus some constant c. Now you might be wondering where that constant c went when we were doing integration with limits of integration. Well, if you were to plug in the upper limit and evaluate that expression and the lower limit and evaluate that expression and take the difference, the c's cancel out. So basically what we're saying is the antiderivative capital F of x plus any constant c, when we differentiate that, we're going to get lowercase f of x. So indefinite integrals have no limits of integration. They do not result in a numerical result. In other words, you're not going to get a number. And they are equal to a family of functions of the form capital F of x plus c, where capital F of x is the antiderivative of lowercase f of x. So let's take a look at an example of that. An example of that might be something like this. The integral of x squared minus sine x dx. So we're going to find the antiderivative of that, which is going to be 1/3 x cubed plus cosine x plus a constant c. If it's an indefinite integral, you have to add the constant c in there. For properties of indefinite integrals, take a look at your textbook on page 349 and you will find this table or properties of indefinite integrals. And it's going to be very, very similar to the properties of definite integrals that we talked about in chapter 5. So how can we ensure that we've done this integral or found this indefinite integral correctly? We can ensure that by differentiating our solution. So if we differentiate our 1/3 x cubed plus cosine x plus any constant c, we are going to get x squared minus sine x, and the derivative of the constant is going to be 0. So we can verify our indefinite integrals by differentiating the solution and seeing that we get back to the integrand that we started with. The next thing we're going to talk about is integration by substitution. And basically the idea here is to be able to find an indefinite or definite integral without having to find the antiderivative of something that is very complicated. So as an example, let's say we have something like this. Sine of x e to the cosine of x dx, and I want to find the indefinite integral there. Upon first inspection, I have no idea what the antiderivative of that is, but if I look at the individual parts, I know the antiderivative of the cosine, or sorry, of the sine is negative cosine. I also know that the antiderivative of e to the x is e to the x. Now where it gets a little bit complicated is what's the antiderivative of e to the cosine of x. So let's separate this by doing some substitution and making things easier. So what we're going to do is we're going to let u equal cosine of x. Okay, and why did I pick that? Well, you'll see in just a minute, and this is the tricky part where you need to practice this to get better at this, to see what substitutions to make. So if u is cosine x, then we know that du dx is equal to negative sine of x, which means that du is equal to negative sine of x times dx. What we're trying to do is we're trying to write our original integrand up here, sine x times e to the cosine x, in terms of the variable u. To make that a little bit easier, I'm simply going to rearrange the order of the integrand and write it as e to the cosine of x times sine of x dx. And what you might see here is that sine x dx is equal to the opposite of du, and e to the cosine of x could be written as e to the u. So this integral can now be written as the integral of e to the u times the opposite of du, but I'm going to write that as du and put the opposite out here. And now this is easy to find the antiderivative of. The antiderivative of e to the u is simply e to the u, and then we have to put our plus c on there, and don't forget the negative sign. Now you might say, well, why didn't we distribute the negative sign to the constant? Because the constant could be positive or negative. It does not matter. Then, when we get done with that, we need to substitute back. So we're going to rewrite this as the opposite of e to the cosine of x plus c. And that is our solution. Now, again, we can check that by finding the derivative. So the derivative of the opposite of the cosine, e to the cosine of x, the opposite of e to the cosine of x plus c is going to be equal to, well, the negative comes out, we repeat the e to the cosine of x, and we multiply by the derivative of the cosine of x, which is negative sine of x, and the negatives cancel out, and we get our original integrand, which is sine x times e to the cosine of x, and the derivative of the constant c is simply 0. So this is, again, not something that is picked up quickly. It takes practice. So let's do a different example with non-trigonometric functions. So let's say we want to integrate the following: x squared square root of 5 plus 2x cubed dx. Again, I have no idea what the antiderivative of that is, but I'm thinking about substitution here. And when I think about substitution, I think about trying to replace maybe the most difficult part of the integrand, but also looking at things like, oh, if I differentiate 5 plus 2x cubed, I'm going to have a 6x squared, and there's an x squared outside the radical. So I'm just going to try the following substitution. I'm going to let u equal 5 plus 2x cubed. So du dx would then be equal to 6x squared, which means du is equal to 6x squared dx. Or another way you could say that is 1/6 of du is equal to x squared dx. So again, I'm going to rearrange the order of my integrand because it's simply multiplication. I'm going to write it as the square root of 5 plus 2x cubed times x squared dx. All right, well, I know that I can replace x squared dx with 1/6 du, and I can replace the square root of 5 plus 2x cubed with the square root of u. So my integral becomes the integral of the square root of u times du. I'm going to take the 1/6 and put it outside, which I would then rewrite as 1/6 times the integral of u to the 1/2 du, and that is easier to find the antiderivative of. All right, so let's leave the 1/6 outside and let's figure out what we have to differentiate to get u to the 1/2. Well, we know the exponent is going to have to increase by 1, so add 1 to 1/2, we get 3/2. If we were to differentiate that, we would end up with the 3/2 coming down, and we want that to cancel, so we're going to put a 2/3 there, and then we put our plus c. So that is our antiderivative in terms of the variable u, and you can verify that if you want to differentiate that to find that you get 1/6 u to the 1/2. So we should probably simplify this and get 1/6 times 2/3. U is equal to 5 plus 2x to the third, so 5 plus 2x to the third to the 3/2 power plus our constant c. And you can distribute the 1/6 if you like, and simplify that or reduce it with the 2/3. The c, you don't have to write it as 1/6 c, you can just leave it as c because 1/6 of a constant is still a constant. But if you want, you can verify that by differentiating that final answer and verifying that we get back to our original integrand, x squared times the square root of 5 plus 2x cubed. So just to illustrate that, let's go ahead and differentiate that. D dx of this whole thing, 1/6 times 2/3 times 5 plus 2x cubed to the 3/2 power plus a constant c. And so let's see, we can bring the constants outside if we want to, but let's not. Let's just leave this the way it is. So we've got 1/6 times 2/3 times 3/2 times 5 plus 2x cubed to the 1/2 power times, don't forget the chain rule here, 6x squared plus c. And again, I left the 1/6 off the c because 1/6 of a constant is still a constant. The 6 and the 1/6 cancel out, the 2/3 and the 3/2 cancel out or reduce, and we get 5 plus 2x cubed to the 1/2 power times x squared, which is our original integrand that we had. So I want to end this video with some suggestions for how to use substitution, or what is often called u substitution or u sub. First thing is, look for a substitution that replaces part of the integrand, the function that you are actually integrating. What is left of the integrand should be some multiple of the derivative of your u substitution. So in other words, if we go back to this example, this last example we did, our u substitution was 5 plus 2x cubed, and du is equal to 6x squared dx. So that's some multiple of the differential, or 6x squared is a multiple of du dx. If the integrand is a quotient, we haven't done any of those yet, but if it's a quotient, a fraction, often the substitution replaces the denominator. Sometimes a trig substitution should be used to replace all or part of the original integrand before using u substitution. We'll show some examples of that later on. And if the integral is a definite integral, we haven't talked about this yet, and you use u substitution, you're going to replace the limits of integration using the equation that relates u to the other variable, or you're going to have to go back to the original variable and not replace the limits of integration. More on that in the next video.